Swayam Prabha. Digital India. Educated India.
Welcome to lecture 29 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Estimation of SUR models and Nonlinear SUR models. In the last lecture, we have discussed how to explain various economic phenomena. You require a set of equations instead of a single equation, and then those set of equations have some kind of correlation between them. Then you have two options, either to estimate different equations of the set of equations separately, or you pool all those equations and estimate the equations jointly. We discussed such kind of models, which are also known as seemingly unrelated regression models, and then we discussed a special case of seemingly unrelated regression models in which you have just two equations. In this lecture, we are going to generalize that case for more than two equations. Say, suppose you have m equations in your model, then how to estimate the coefficients of those m equations. We will also discuss nonlinear seemingly unrelated regression models, how to estimate the nonlinear seemingly unrelated regression models. So, now we consider the general case of m equations. So, you have m equations like y 1 equal to x 1 beta 1 plus u 1, y 2 equal to x 2 beta 2 plus u 2, so on y m equal to x m beta m plus u m. Again, just like the previous case, we assume that expected value of u small m is equal to 0, expected value of u m transpose is equal to sigma for all small m equal to 1 to so on capital M. Then y m is of order n cross 1, x m is of order n cross k m. So, in the mth equation you have k m explanatory variables. Beta m is of order k m cross 1 and u m is of order n cross 1. Now, we pull all these equations. So, we write y equal to y 1, y 2, so on y capital M. So, this y is of order n m cross 1. Then we have x equal to, say we have x 1 here, then 0, 0, so on 0, then 0, x 2, so on 0 and so on 0, 0, so on x m. So, here you have k 1 columns, then k 2 columns, so on k m columns, then n and so on n. So, the order of this X matrix is n m cross summation k m, m equal to 1 to capital M. Beta is beta 1, beta 2, so on beta capital M, and u is equal to u 1, u 2, u m. Then we can write all the capital M equations jointly as y equal to x beta plus u. Again, expected value of u is 0, expected value of u transpose is equal to, actually you have u transpose and then you take expectation and then you are writing u equal to u1, u2, so on um. And then you have u1 transpose, u2 transpose, transpose. So, you get expected value of u1 transpose, u1, u2 transpose, so on u1, transpose and so on u1 transpose, u2 transpose and so on transpose, and then we take expectation. So, expectation of u1 transpose is equal to sigma, then expectation of u1 transpose is equal to sigma 1 I n. Expectation of u2 transpose is sigma 1 2 I n and so on. So, ultimately you obtain expected value of u transpose is equal to capital sigma Kronecker product I n. And then for estimating beta you can apply GLS procedure. So, the GLS estimator of beta is beta hat equal to x transpose sigma inverse Kronecker product I n x inverse x transpose sigma inverse Kronecker product I n y. Because if you denote this variance covariance matrix by V, then V inverse is equal to sigma inverse Kronecker product I n. And actually beta hat is equal to x transpose V inverse x transpose V inverse y, and then we replace V inverse by sigma inverse Kronecker product I n. So, you get this estimator. Now, suppose sigma superscript I j is the ijth element of capital sigma inverse. Then expanding the Kronecker product, we obtain beta hat equal to this. You get this expression for beta hat. Simply you have to expand the Kronecker product and then you write sigma inverse equal to, so sigma I j. Now, from this expression you observe that when sigma I j is equal to 0 for all I not equal to j, then the GLS estimator of beta reduces to the OLS estimator B equal to B1, B2, Bm, where B small m is equal to xm transpose xm inverse xm transpose ym. So, you have obtained this Bm by applying OLS to the mth equation. The mth equation is ym equal to xm beta m plus um. So, you have applied OLS to the mth equation and then you get this estimator. So, actually this result shows that if the covariances between different equations are 0 or if in the set of equations different equations are uncorrelated with each other, then the GLS estimator reduces to the OLS estimator. And it seems logical also, because in that case this mth equation can be estimated separately, and if you estimate this equation separately, then you are not going to lose any information. The other equations are uncorrelated with this equation. So, it means the other equations do not have any information about this equation. So, there is no purpose of pooling. It will not serve any purpose. You get the same information if you estimate different equations separately, or if you estimate all the equations jointly after pooling all the equations. To prove this result, suppose you take sigma I j equal to 0 for all I not equal to j, then sigma I, sigma superscript I, which is the ith diagonal element of sigma inverse, is simply sigma I inverse, because in that case sigma is equal to sigma 1 1 0 0 0 sigma 2 2 0 0 0 sigma m. So, obviously, sigma inverse is equal to sigma 1 1 inverse, sigma 2 2 inverse, so on, sigma m inverse, and here you have 0. So, ith diagonal element of sigma inverse is sigma I inverse, and sigma superscript I j means the ijth diagonal the ijth element of sigma inverse is 0 for all I not equal to j. Then the expression for the GLS estimator becomes, just look here, the expression for GLS estimator. This term is 0 and so on, all these terms are 0. So, here you have sigma 1 1 x 1 transpose x 1, and this sigma 1 1 is equal to sigma 1 1 inverse. Similarly, this sigma 2 2 sigma superscript 2 2 is equal to sigma 2 2 inverse, and so on. Then here for j equal to 1, you get sigma 1 1 inverse x 1 transpose y 1, and for j equal to 2 you get 0, for j equal to 3 you get 0, and so on. Here for j equal to 1 you get 0, for j equal to 2 you get sigma 2 2 inverse x 2 transpose y 2, and so on. So, finally, you get the expression for beta head as this. And then we multiply these two equations. The inverse of this is sigma 1 1 is equal to sigma 1 1 inverse, and then if we take inverse, then you get sigma 1 1 into x 1 transpose x 1 inverse here. After taking this inverse, here you get sigma 2 2 x 2 transpose x 2 inverse, and so on, sigma x m transpose x m inverse, and then you have sigma superscript 1 1, which is equal to sigma 1 1 inverse, then x 1 transpose y 1, and when we multiply it, then you get x 1 transpose x 1 inverse, x 1 transpose y 1 here, which is equal to b 1. Here you obtain sigma 2 2 x 2 transpose x 2 inverse, and then you have sigma 2 2 inverse, sigma superscript 2 2 is equal to sigma 2 2 inverse x 2 transpose y 2. So, finally, you obtain b 2 here, and so on, you get b m here, where small b m is the OLS estimator of beta m based on the mth equation. Next result is when x 1 is equal to x 2 so on equal to x m, then the GLS estimator becomes the OLS estimator. So, suppose we take x 1 equal to x 2 so on equal to x m equal to z. So, the matrix X is equal to z 0 so on 0 and so on 0 0 so on z. So, you can write X as I m canonical product Z, and then x transpose sigma inverse canonical product I n x is equal to I m canonical product Z, then you take transpose of this, you take transpose of x. So, you get I m canonical product Z transpose, then in between you have sigma inverse canonical product I m, and then you have I m canonical product Z. So, what you get? You get I m into sigma inverse, which is sigma inverse canonical product Z transpose into I n. So, you get Z transpose here, and then you have I m canonical product Z here. So, finally, you obtain sigma inverse canonical product Z transpose Z. You got this term. Then x transpose sigma inverse canonical product I n y is equal to, again we write x transpose equal to Z transpose, then you have I m here. So, I m canonical product Z transpose, then you have sigma inverse canonical product I n y, and then this is equal to sigma inverse canonical product Z transpose y. So, x transpose sigma inverse canonical product I n y is equal to this. Then the GLS estimator beta hat is equal to sigma inverse canonical product Z transpose Z whole inverse sigma inverse canonical product Z transpose y. We take this matrix and multiply it by this one. So, you have inverse of this matrix and then this one. Then inverse of sigma inverse canonical product Z transpose Z is equal to, this is actually equal to sigma inverse canonical product Z transpose Z inverse. Then you have, you are taking inverse. So, you get sigma canonical product Z transpose Z inverse. Then you have sigma inverse canonical product Z transpose y, and then this is equal to, you get identity matrix here, canonical product Z transpose Z inverse Z transpose y, and then we write y equal to y 1 y 2 y m. Now, Z transpose Z inverse Z transpose y small m will give you B m. So, here you get B 1 B 2 B m now. So, the result follows. B m is the OLS estimator of beta m based on the mth equation. So, in case you are using the same set of explanatory variables in all the equations with same observations, means you are using the same set of explanatory variables with same observations in all the equations, then it is not worth to pool all the models. Your GLS estimator is same as the OLS estimator. So, you are not getting any extra information in this case. Now, we consider the case when sigma is unknown. So, we obtain the feasible generalized least squares estimator. Here we consider two different estimators for estimating sigma. The first estimator is based on the unrestricted residuals. So, we make use of unrestricted residuals for estimating sigma. Suppose capital K star is the total number of distinct explanatory variables out of k 1, k 2, k m variables in the full model. So, the entire model has k 1 plus k 2 so on plus k m variables, but out of these variables some of the variables may be common. So, suppose there are k star distinct explanatory variables in the model, and here capital Z denotes n cross k star observation matrix of these variables. Then we regress each of m study variables on the column of Z and obtain n cross 1 residual vectors u I hat equal to y I minus z, z transpose z inverse z transpose y I. So, we take y I and run regression between y I and z, and then we obtain the residual u I hat. So, u I hat is equal to y I minus z, z transpose z inverse z transpose y I, and we write it equal to say h z bar y I for all I equal to 1 to m, where h z bar is equal to I n minus z, z transpose z inverse z transpose. Now, we obtain S I j equal to 1 upon n u I hat transpose u j hat, and then this is equal to 1 upon n y I transpose h z bar y j. Remember that this h bar z, this is an idempotent matrix. And this is symmetric also. So, square of this matrix is h bar z. So, you take S I j equal to 1 upon n y I transpose h z bar y j, and then we construct the matrix S equal to the I jth element of S is S I j. Now, this X I is a submatrix of Z. So, obviously, you can write X I equal to Z J I, where J I is a k star cross k I selection matrix, means it has sum of the elements equal to 1 and sum of the elements equal to 0, and we choose the elements of J I in such a manner that it picks X I from Z. So, that is why Z I is called the selection matrix, and it is of order k star cross k I, means X I is of order n cross k I, Z is of order n cross k star, and J I is of order k star cross k I. And then h bar z x I is equal to x I minus z, z transpose z inverse z transpose x I, and then this is equal to x I minus, you have z j I, which is equal to 0. You simply write x I equal to z j I. So, you get z transpose z j I, and then z transpose z inverse z transpose z is equal to identity matrix. So, ultimately you get z j I, and z j I is equal to x I. So, you get x I minus x I, which is equal to 0. So, y I transpose h bar z y j can be written as, we write y I equal to x I beta I plus u I. So, y I transpose is equal to beta I transpose x I transpose plus u I transpose h bar z x j beta j plus u j, and then this is equal to u I transpose h bar z u j. Now, we take expectation of S I j. Expectation of S I j is equal to 1 upon n expectation of u I transpose h bar z u j, and then you can write it as, so we obtain this expectation u I transpose h bar z u j. So, you can write it as expectation of trace of h bar z u j u I transpose, and u j u I transpose is equal to sigma 1 I j identity matrix. So, you get sigma I j trace of h bar z. So, you get this, and trace of h bar z is equal to n minus k star. This you can easily verify. Remember, h bar z is equal an idempotent matrix, and h bar z is equal to I minus z, z transpose z inverse z transpose. So, trace of h bar z is equal to n minus k star, or expected value of n upon n minus k star S I j is equal to sigma I j. So, if you take the estimator sigma head I j equal to n upon n minus k star S I j, which is equal to u I head transpose u j upon n minus k star, then this is an unbiased estimator of sigma I j. Then the feasible GLS estimator of beta is beta head equal to x transpose sigma head inverse canonical product I n x whole inverse x transpose sigma head inverse canonical product I n y. So, we simply replace sigma by its estimator here. Now, we consider the second estimator of sigma, which is based on the restricted residuals. So, in this estimator we use restricted residuals for estimating sigma. And in this estimator we regress y I on x I for each of the equation I equal to 1 to capital M, and then we obtain the OLS residual vector u I curl equal to I minus x I transpose x I inverse x I transpose y I, which is equal to h bar x I y I, where h bar x I is equal to I minus x I transpose x I inverse x I transpose. Then a consistent estimator of sigma I j is obtained as, say, S I j star equal to 1 upon n u I curl transpose u j curl, and then this is equal to, actually you have u I curl equal to h bar x I y I and u j curl equal to h bar x j y j. So, you obtain y I transpose h bar x I, because h bar x I is a symmetric matrix. So, you get the same matrix if you take the transpose, then h bar x j y j. So, these are the expressions for h bar x I and h bar x j. Then using S I j star, a consistent estimator S of sigma can be constructed. We simply replace sigma I j by this estimator in the expression for sigma. So, you get S, which is a consistent estimator of sigma. Further, if you take expectation of y I transpose h bar x I, h bar x j, y j, this is equal to, just like the previous case, you can obtain this expectation you write it as expectation of u I transpose h bar x I h bar x j u j, because say h bar x j into x j is equal to 0, and similarly h bar x I into x I is also 0. So, you get this expression, and then you write it equal to expectation of trace of say h bar x I h bar x j u j u I transpose, and then we take expectation inside. So, expectation of u j u I transpose is equal to sigma I j I n. So, you take sigma I j outside, and inside you get trace of h bar x I h bar x j. Then trace of h bar x I into h bar x j can be obtained as, say you have sigma I j here, then n, because in the beginning you have identity matrix of order n. So, you get I n here, trace of I n is n, minus you get the term, if you take h bar x I into h bar x j, you get I n minus x I transpose x I inverse x I transpose minus x j transpose x j inverse x j transpose. You take trace of this, you get k I. If you take trace of this, you get k j, and then you have plus a cross product term, trace of x I transpose x I inverse x I transpose x j transpose x j inverse x j transpose x I. You get this term also. And then an unbiased estimator of sigma I j can be obtained as, say S I j curl equal to u I curl transpose u j curl divided by n minus k I minus k j plus trace of this term. And this is an unbiased estimator of sigma I j. Now, we obtain the maximum likelihood estimator for the parameters. Then for obtaining the maximum likelihood estimator, we consider the tth observation on each of m dependent variables and corresponding regresses, and then arranging these observations horizontally, we can write the model in this form, say y 1, y 2, so on y m t equal to say x t star transpose pi 1, pi 2, pi m plus u 1, u 2, u m t. So, this is corresponding to the tth observation. Or you can write capital Y equal to x star pi transpose plus u. Here actually x t star is the set of k star different explanatory variables. So, some of the explanatory variables may be common to all the equations. So, you consider the set of k star different explanatory variables, and then you arrange those observations horizontally, and then you get this vector x t star. Similarly, you get this vector y 1, y 2, y m t, and then we combine all the observations and we get this relation y equal to x star pi transpose plus u, where this y is of order n cross m, u is of order n cross m, then x star is of order n cross k star. Now, pi transpose has one column for each equation and the ith column is pi I. Then pi I has number of zeros in it, each one imposing exclusion restriction. Just to clarify this point, let us take this example. So, suppose you have two equations y 1 equal to alpha 1 plus beta 1 1 x 1 plus beta 1 2 x 2 plus u 1, and the second equation is y 2 equal to alpha 2 plus beta 2 2 x 2 plus beta 2 3 x 3 plus u 2. So, x 2 is common to both. Then intercept term is also common. Now, then corresponding to the tth observation, you have y 1 y 2 t equal to, you have 1, then you have x 1 here, then x 2, and then you have x 3. So, you do not take x 2 two times, x 2 is common to both the equations, and then corresponding pi matrices of the form, say you have alpha 1, beta 1 1, beta 1 2 and 0. We take 0 here because x 3 is absent in the first equation. So, we impose this restriction here, we take this element equal to 0. So, we are imposing exclusion restriction. Then corresponding to y 2, you have alpha 2 here, then x 1 is not here in the second equation. So, we take 0 here, we impose this restriction. The corresponding coefficient, the coefficient corresponding to x 1 is 0. Then corresponding to x 2 you have beta 2 2, corresponding to x 3 you have beta 2 3 plus u 1 u 2 t. So, this is how we arrange all the observations. Then log of joint normal density of m disturbances is log L t equal to minus m by 2 log of 2 pi minus 1 by 2 log of determinant value of sigma minus 1 by 2 u t transpose sigma inverse u t. And then we have n observations for t equal to 1 to n. So, log likelihood is log of L equal to minus m n by 2 log 2 pi minus n by 2 log determinant value of sigma minus 1 upon 2 summation t equal to 1 to n u t transpose sigma inverse u t. So, we get this log likelihood function under the assumption of normality of disturbances, and then we write it as say minus n by 2 m log 2 pi plus log determinant value of sigma plus trace of sigma inverse w, where w is the matrix with element w I j, and w I j is defined as 1 upon n summation t equal to 1 to n u t I u t j. So, we write the log likelihood function in this form, and then we differentiate this log likelihood function with respect to pi transpose, and we put it equal to 0, and this implies that say you have this part here, if you differentiate this part or this part, then you get 0, and remember u t I is equal to, you get the expression for u t I from here, or in the expression for u from here, u is equal to y minus x star pi transpose. So, you get x star transpose sigma inverse u equal to 0. And then if we differentiate the log likelihood function with respect to sigma and put it equal to 0, then you get sigma inverse sigma minus w sigma inverse equal to 0. Actually, for obtaining this expression, we have utilized these results. Say if you differentiate trace of sigma inverse w with respect to sigma, then you obtain minus sigma inverse del over del sigma inverse trace of sigma inverse W sigma inverse, and this is equal to minus sigma inverse W sigma inverse. And the differential coefficient of log of determinant value of sigma with respect to sigma is equal to sigma inverse. So, we have utilized these results and then we get this equation. And then we have also utilized this result. If we differentiate trace of sigma inverse W with respect to pi transpose, then we get 1 upon n del over del pi transpose trace of y minus x star pi transpose is sigma inverse y minus x star pi transpose. And then if we differentiate it with respect to pi transpose, then we obtain minus 2 upon n x star transpose sigma inverse u, and u is equal to y minus x star pi transpose. So, you can easily verify it. And then from equation 10, given slope parameters, the MLE of sigma is W. So, if pi is given, then you can obtain the MLE of sigma. Then replacing sigma by W in it, the concentrated log likelihood function is log LC is equal to minus n by 2 m log 2 pi plus log determinant value of W plus m. We have simply replaced sigma by W here. And then from here you obtain beta hat ML equal to minimum over beta half log determinant value of W, subject to the exclusion restriction. As such, it is not possible to find the exact expression for the maximum likelihood estimator beta hat ML, but if we obtain the minimum over beta of 1 upon 2 log of determinant value of W, then it leads to the maximum likelihood estimator, and we minimize it subject to the exclusion restrictions, means subject to the restrictions that sum of the coefficients are equal to 0. Now, one can also define the goodness of fit measure R square as suppose u hat is equal to y minus x beta hat, where beta hat is the FGRS estimator of beta. Omega hat is equal to sigma hat canonical product I n, and yi bar is equal to 1 upon n summation yi l equal to 1 to n. Then sigma hat superscript I j is the I jth element of sigma hat inverse, and then we define S I j equal to 1 upon n summation y I t minus y bar I y j t minus y bar j, and S y y is the matrix with I jth element S I j. Then again I am not going into the details of this expression, but R square is defined as 1 minus, in the numerator actually we take the residual sum of square, in the denominator we take the total sum of square. So, we have u hat transpose omega hat inverse u hat divided by summation I equal to 1 to m summation j equal to 1 to m sigma hat superscript I j, which we have defined here the I jth element of sigma hat inverse, and then we have summation t equal to 1 to n y I t minus y bar I y j t minus y bar j, and then this summation is actually equal to n times S I j. So, actually you get 1 minus then omega hat is equal to sigma hat canonical product I n, and sigma hat is defined on the basis of this u hat, and actually you obtain m here. If you take u hat transpose omega hat inverse u hat, then you get m divided by, in the denominator we get trace of sigma hat inverse S y y, we get S y y if we use this relation. So, we get this expression for r square. Again, for testing the linear hypothesis of this form, h r beta equal to small r, where r is of order q cross k m, small r is of order q cross 1, beta is of order k m cross 1, and capital K is summation small k m. The F ratio is defined as F q m n minus capital K equal to, you take r beta hat minus small r transpose r x transpose omega hat inverse x r transpose whole inverse r beta hat minus small r divided by q in the numerator divided by u hat transpose omega hat inverse u hat upon m n minus capital K you have in the denominator. Then for large sample n, we get the Wald statistic q f hat equal to r beta hat minus small r transpose r variance of beta hat r transpose inverse r beta hat minus small r. So, you can use this test statistic or this test statistic. For large sample, this follows chi-square distribution with q degrees of freedoms. Again, when this calculated value is greater than the tabulated value of f at say alpha level of significance, we reject H naught, otherwise we accept H naught. So, you can use this test statistic or this test statistic for testing the set of linear hypotheses. Now, we consider non-linear seemingly unrelated regression models. So, we consider the non-linear system of equations, say y 1 equal to h 1 beta x plus u 1, y 2 equal to h 2 beta x plus u 2, so on y m equal to h m beta x plus u m, where y m is of order n cross 1 and beta is of order k cross 1. X L for L equal to 1 to k is of order n cross 1 and these are k independent variables. Then some or all of them appear in each equation. So, it may happen that some of the variables which are appearing in the first equation may not appear in the second equation or may not appear in the third equation. So, different sets of independent variables may appear in different equations. Then u m for all m equal to 1 to capital M, these are the disturbances having mean 0 and covariance matrix capital sigma. Now, when sigma is known, the GLS estimator can be obtained by minimizing u beta transpose omega inverse u beta, which is equal to summation I summation j sigma superscript I j y I minus h I beta x transpose y j minus h j beta x. This sigma superscript I j is the I jth element of capital sigma inverse, and u beta is m n cross 1 vector of disturbances, and this vector of disturbances is obtained by stacking all the equations. Then just like what we did in lecture 27, for the single equation we use the Taylor series expansion and then we obtain the first order conditions for minimizing the sum of squares this. So, we differentiate u beta transpose omega inverse u beta with respect to beta and then we obtain this equation summation I summation j sigma I j twice x I naught transpose beta u j beta equal to 0. So, we are following the same steps which we have followed in lecture 27. Then x I naught beta is n cross k matrix of pseudo regressors. We defined similar kind of pseudo regressors in lecture 27 also. and if any of the parameters beta do not appear in the ith equation, then corresponding column of xi naught beta is taken as 0. Now, in practice sigma is unknown. So, we proceed like this. In first step, we estimate parameters of each equation separately using non-linear least square procedure, and then the resulting residuals, say u hat, can be used to estimate sigma. So, initially we have applied non-linear least square to each of these equations, and then on the basis of obtained residuals u hat, we have obtained capital S, the estimator of sigma. In step 2, we obtain FGLS, then we solve equation 11 iteratively replacing sigma by S. So, in equation 11, we just replace sigma by S and then we obtain the solution. And then asymptotic covariance matrix of FGLS estimator is estimated by this quantity. Say estimate of this asymptotic variance covariance matrix is summation I summation j S I j x I naught beta transpose x j naught beta whole inverse. So, we apply this iterative procedure for obtaining the FGLS. Then for our first step, we can obtain beta by minimizing this quantity. This step will provide beta hat required to compute S. We can also apply GMM procedure for estimating the parameters. Say suppose in model 9 xi t naught and ui s have non-zero correlation, and z t be a set of instrumental variables such that expectation of z t u I t is equal to 0 for all t and for all I. Then sample analog of this equation is 1 upon n summation over t z t, and then we replace u I t by y I t minus h I beta x t equal to 0. Then using equation 15, we get the GMM estimator for each of the equation, and then we are neglecting the correlation between the disturbances. It results in efficiency loss. Here we have not used the correlation between different equations. And then we take 1 upon n z transpose omega I j z equal to expectation z transpose u I u j transpose z upon n. Then the GMM criterion for estimation is in setting 16 is we take q equal to summation I summation j 1 upon n y I minus h I beta x transpose z. So, we consider this quantity, and in between we take 1 upon n z transpose omega I j z I j. This is the I jth element of inverse of this matrix, and then 1 upon n z transpose y I minus h I beta x. And so, you replace y I minus h I beta x by u I beta, here we get this quantity. So, you can use this criterion for obtaining the generalized GMM estimator. So, again I am not going into the details of this technique, but you can obtain the GMM estimator for the parameters using this technique. So, in this lecture we have considered the case of m equations seemingly unrelated regression model, and then we have derived the GLS estimator and FGLS estimator for the regression parameters as well as the maximum likelihood estimators also. Then we have also considered the non-linear seemingly unrelated regression model, in which each equation is a non-linear regression. You have a set of non-linear equations which form a non-linear seemingly unrelated regression model, and then we have discussed the estimation procedure for non-linear seemingly unrelated regression model also. So, I am going to stop here. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I am with the Department of Humanities and Social Sciences at IIT Kanpur. Today I am going to talk about what is social cognition. Social cognition is a research area in psychology which explicates the various cognitive processes that people employ to understand the social world. So, essentially it is about sense making of the social world, which involves understanding other people as well as understanding oneself. Understanding others requires understanding their traits, their internal tendencies, their contextual aspects, motives, feelings, emotions, etc. So, as we can see, this is a very complex process and requires a massive amount of information processing. Even for small decisions, for simple decisions, people have to process a large amount of information. The main perspective or the approach which is used in social cognition is obviously the cognitive approach, and which is the study of mental structures and processes. The main paradigm which is used is the information processing paradigm. As far as the range of topics in social cognition is concerned, the range is very wide, from individual level sense making to collective sense making. As far as views of cognitive sense making are concerned, there are three major dominant views in social cognition: the naive scientist view, the cognitive miser view, and the motivated tactician view. The naive scientist view emerged from research done in causal attribution, and this refers to detailed and systematic processing of information and sense making in the social world. However, it is not always possible to make detailed engage in detailed cognitive processing, and hence people act as cognitive misers in many situations. So, whenever there is lack of time and cognitive effort is less, then people involve in using certain strategies which are functional, yet they are like mental shortcuts. So, this is the cognitive miser approach. However, the question that comes to the fore is that which one of the two strategies is more important? The answer is provided by the motivated tactician view. And according to this view, people can either use the naive scientist approach or the cognitive miser approach as and when required, and they can switch over between the two approaches when required. So, these are the three major views which are utilized to understand cognitive sense making. The topics that social cognition covers ranges from cognitive social cognition to social cognition. So, topics such as causal attribution, understanding of attitudes, social schemas, unconscious cognition about social situations, the use of mental shortcuts or heuristics in decision making, social identity, and stereotyping processes are some of the topics. In addition to this, a large number of social cognitive psychologists also understand collective sense making in terms of social representations.